Hey guys, and welcome to a brand new chapter in your math careers. This one's all about functions. Functions, you know them, you've seen them before. In this chapter, we're really going to get into different types, what they are, and what they can do for you. So it's a very useful chapter. So functions, as you know, you have x and y values, dependent and dependent. Basically what they do is you have some independent variable like the number of muffins you sell, and you put it into the function, and that spits out a new value for you, like how much money you made that day from muffin sales. So that's basically what they are. But how do we create these functions, and how do we apply them to real life? So that's really what this chapter is all about. They can predict a lot for us, not only profits, but sports scores, weather, anything you have data on up from the past, you can use that to make predictions about the future, or predictions about different amounts. So if you have data for all these different temperatures, and you want to know, well, how fast can I run in those temperatures, you can create a spread and make predictions. So very useful, very fun. Basically what these functions are, it's just a special relationship between two things. I wrote things here, but really what we're talking about is two variables. Two variables. And when you write a variable, naming your variables, identifying your variables, I'm giving you a tip right now. Put it in the format, the something of something. So it should be the cost of rent, the number of bananas, the time of cooking. If you have it in this form, then you know you're doing something right. Because if you just write elephants, well, I don't know. Is that the weight of the elephants, the height of the elephants, the cost of an elephant, the lifespan of an elephant? What about the elephants are you actually measuring? What's the number mean? So make sure it's in this form and you'll be sitting pretty. So let's take a look at this first sentence here. How much money you make and how many hours you work. So say you make an hourly wage. How do these two things relate? Well, how much money you make depends on how much you work, how many hours you work. Excuse me. So we would say that our dependent variable, the one that depends on the other, and I'll write this out, dependent variable. Well, which one depends on the other one? That would be the money, or I should say the amount of money made depends on, we'll call that our x value, our independent variable, the one that does not depend on the other, and in this case our independent variable will be how many hours you work. So I'm going to write number of hours. So notice I kept it in this of format, and then I know what I'm talking about. Okay, so identifying your variables is very important. Let's do one more example. Your speed of your car versus how much you push on the gas pedal. Well, again, the first one depends on the second. The speed of your car depends on how much you push on the gas pedal. So your dependent variable is going to be the speed of the car, and your independent variable is going to be the amount the pedal is pushed. Now, obviously there's no of in this little phrase, but that's okay. It's still very clear. It's the amount the pedal is pushed. So this might be measured in centimeters or something like that. Just how far down does the pedal go? So that's just a nice little exercise to get us back into thinking about two variables, and we're trying to find a relationship between them. So a relation in math, a relation is the word we use for any mathematical relationship. So the centimeters, how many centimeters you push down on the gas versus the speed of your car, those things have a relationship. A function is a special mathematical relationship, so a special kind of relation where there is only one dependent variable for every independent variable. So what does that mean? It means for any given value of x, there is only one value of y that goes along with it. So if you put in that you pushed on the gas 2 centimeters, well, there's only one number that could possibly come up. Let's say it was 10 kilometers per hour. It wouldn't be 10, but also it could also be 20. It could also be going backwards 10, so negative 10. There's only one value. If that's the case where there are unique pairs like this, 2 and 10, then that is a function. And we'll talk a little bit in a second about how to identify these from a graph. The third one, which often gets forget but is very important, is an inverse, or an inverse relation. So this is a relation you get when you switch the values of every ordered pair. So you take the x and you take the y and you switch them. So that's the first one we're going to get into. We're going to sort of go backwards here, starting with the inverse relation. So before that, we will talk about, is it a function or just a relation? So I say just a relation because if it's a function, then that's a special kind of relation. So what I'm going to use here is what I call the vertical line test. And I'm going to use my trusty ruler as a vertical line, but you can just imagine one or use a pencil, whatever it may be. So the test is, it will be a function if it only touches the vertical line once. So the vertical line test states that a function only crosses the vertical line once. So what would this mean if, we have a little technical issue, once. If it only crosses it once, that means for every x value, there's only one y value, which is the definition of a function. So let me shorten my ruler here and get started. This first one here, I'm going to scan along this function. That means I'm going through all the x values. And for every x value that I pass by, I'm seeing that there's only one y value. It only crosses the line once, which means that this is indeed a function. So, good stuff. We got a function here. Okay. What about this second one? Same test, traveling along the x-axis, seeing, looking, so far so good. There's only ever one y value for every x value, and so this too we can call a function. It gets that special name. Here's something you may or may not have seen before. I'm traveling along and whoops, what's this? An open dot under a solid dot. This too means there's only one dot here. It means that this open dot, there is no value here. There is no value here. It is disconnected from this line, yes, but at this point, this one, I can line up my ruler with it. At this value of x, whatever it might be, there is only one value of y right there. So it passes the vertical line test. We can say that this is indeed a function. Okay, so far so good. 3 functions in a row. Let's see about this guy. Traveling along, whoops. I'm seeing that here and here, there are 2 places where for one x value, we cross the line. So there are 2 y values for a given x value. see over here as well, pick this x value, whatever it might be. It crosses here and here. So we plugged in this value of x, we would get 2 answers. So there's not a unique dependent variable for this independent variable. So this one does not pass the vertical line test. So it's not a failure, but it is just a relation. There's a relationship here between x and y for sure, but it's not one that is called a function. What about this? Put it on the x value. Well, in this one, in fact, there are infinite numbers of y values. So this is certainly not a function. This is a relation. So there you go, the vertical line test, something you can use or just imagine to help you determine if something is a function or just a relation. So, as promised, here is the inverse relation. How do we find it? How do we use it? Well, first let's plot these points, okay? So the first point is 1 and 3. That's 1 point. So I'll go to my graph here, 1, and I'm going to go up 1, 2, 3. So here is my first point. Then my second is 2 and 9. So I'll go 1, 2. Here's 2. And then 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So somewhere around there will be my second one. And this is obviously just a very rough sketch. Finally, here's 3. Moving on up. And 13 will be right at the top. 13. So we get something that looks like this, almost a linear function. It's hard to tell, but something that looks like this. And we can try to sketch a straight line between them. Here, I will pick a color. We'll just say something like this. So here's the function, something like that. Well, to find the inverse, I said we switch the x and the y values. So we start with this ordered pair, 1, 3. Well, now x is going to be where the y was, y is going to be the x one, so this value is going to be 3, 1. Here we have 2 and 9. The x was 2, so now the y is 2. The y was 9, so now the x is 9. And similarly, we're going to switch our last point, so it becomes 13 and 3. So let's plot these points to see what it looks like. The first one is 3 and 1, so 1, 2, 3 over, 1 up. Here's the first point. Second one is 9 and 2, so 3, 4, 5, 6, 7, 8, 9, and then 2, 1, 2, so somewhere around here. And the last one, 9, 10, 11, 12, 13, the last dash, and just up to 3. So again, we'll plot this line, see what it looks like, and there you have it. So in fact, what you end up getting is a bit of a flipped graph. You can imagine almost that it is reflected somewhere along this line. We call this the xy line because if you were to graph the function x equals y or y equals x, that would be what it looks like. So it flips it along this axis. It's not really an axis, but along this line of reflection. That's what it looks like. And how do we map the points? Well, simply by flipping the x and the y. So what if we have a rule? How do we do this? Well, I said you just switch the x and y, and that's exactly right. So here we have y equals 3x squared plus 1. What is the inverse relation of this function number 1? Well, it would be x equals 3y squared plus 1. And generally, we want our functions to equal y to be alone, because we're going to plug in an x value, and we want to spit out a y value. So this is a true rule, but generally, we have to then solve for y. So if I'm solving for y, first I will bring over the 1. So we'll have x minus 1 equals 3y squared. I'll divide both sides by 3, so I'll have x minus 1 divided by 3 equals y squared. And finally, get rid of the squared here by finding the square root x minus 1 over 3 equals y. So this would be the inverse rule, but we found that simply by switching the x and the y. That's how we do it. Okay, moving on. The last thing I want to talk about today is properties of functions. So, what are properties of functions? These are a property of anything is something that you use to describe it. That's a property. So, the main ways we describe functions are in this: the domain and range, the variation, extremes, sign, and intercepts. Let's quickly go through each one. Hopefully this is a review for you. So, domain and range. Domain encompasses all x values. So, all independent variables, or values, I should say. Now, this is a interval, so we're going to use square brackets. So the first value, it goes from here to here, right? These are all the x values that are included on this line. So the first value, which is included, is -8. That is the first x value. So I will write include -8, and it goes all the way along until +10, a value which is also included in the set. So included, so the brackets are facing inward for both of them. Range is all the y values, all the dependent variables. So what range of values can you expect given this function? Well, it starts with the smallest y value to the greatest y value. So I will include -4 for this one, and it goes from -4 all the way up to 6. So I will include 6 as well. And this is the range. This interval says we go from -4 all the way up to +6. So there's your little review of domain and range. The variation is talking about increasing, decreasing, and constant. So for this one, we look at and see over what interval is this function increasing. Well, it is increasing over the interval, and we start here. The point where it starts is included in the set, so 4, and notice we're using the x values for this. It starts at the x value of 4, and it increases to 10 over the part of the domain from 4 to 10, this interval. So notice again, we're using the dependent variables. So decreasing, over what interval is it decreasing? Try to find it yourself. Certainly from here to here. So what values shall I put in? If you said -8 to -4, you were right. -8 to -4 is the interval for which this is decreasing. And the last one, where is it constant? Well, it's constant over the interval -4 to +4. -4 to +4. And both values are included, so the brackets are facing inward. Now, the extremes, sometimes called the extremas. I'll write that in red next to it. Extrema. That would be the plural form of extreme. So, the extremes of this are the highest value and the lowest value, also called the maximum and the minimum. And here we are looking for those dependent variables. How much can this thing actually go up and down? So what is the highest y value shown here? Well, it's all the way up here. The highest y value is 6. So the maximum is 6. That's it. We're not looking for an interval here. We're looking for the actual number. How high does this thing go? How low does it go? Down to -4. That's it. So note, the extremes are the extremes, how high and how low. It does not take an interval. You'll also notice these are the values shown in the range. The range was -4 to 6. So they're related. There you go. The sign. Okay. And there's something interesting about the sign of this particular function. We're going to talk about when it's positive and when it's negative. Let's talk about when it's negative first. So, over what interval is this function negative? Well, it becomes negative, it starts being negative at -6. Notice we're using the x values. So, -6, it is beginning to be negative. When it's 0, right here it's at 0, that is both positive and negative. So it's included in both sets. So, -6, and it continues to be negative below the x-axis. Continues to be negative all the way until +6. So it starts being negative at -6 all the way to +6. This is the interval for which you will produce negative y values. So here, all of this has negative y values. So here's the part of the domain, the interval of the domain for which it is negative. Now, the positive one, the positive interval is a little more interesting, something that you may need to be reminded of, because it's broken into two parts. It's positive over here and it's positive over here. So how do we write that? Well, first we write the first interval. It goes from -8 to -6. All the y values corresponding to these x values would be positive. And we write it normally. Then we include a symbol u. U means union. So we are putting these two intervals together. This is how we do it. Write a u. U means union. We are putting these two intervals together. And then you continue from where it becomes positive again. That would be +6 all the way to +10. So make a note to yourself about this u when you need to put two intervals together. The last thing I want to point out is the intercepts. So you have two axes here, an x-axis and a y-axis. The line intercepts these axes. So where do they happen? Well, at the intercepts. They intercept at the intercepts. So the x-intercepts, these are called the zeros. Not because people don't like them, but because this is where the y value is equal to 0. Here it's 4, 3, 2, 1, 0. And what does the x value correspond to here? So in this case we have 2. We have a x of -6 and we have an x of +6. So 2 zeros. And that's it. It's just a number. The y-intercepts are much more interesting in general. We call these the initial values. Why? Because in most real-life situations, this is where your graph would start, at 0. So if this was time, you would start the timer here at 0, and it would continue onwards in a linear function, right? You don't go backwards in time past 0. So in general, that's true. Now, there are obviously a lot of exceptions where you have negative x values, but this is where the convention comes from to call it the initial value. And often you see that in questions. The ball started flying in this direction at this speed. What was its initial speed? Meaning, what was its speed at time equaling 0? So how do we find that? We just look along the y-axis. Here it is It intercepts the y-axis when x is equal to 0, x is equal to 4, 3, 2, 1, 0, and the y is negative 4. So here, our y value is negative 4. So that's all for today's lesson. See you in the next one.